Hi, we are UBC Uncrewed Aircraft Systems, or UAS for short. We are a team comprised of over 70 multidisciplinary students attending the University of British Columbia. This year, our competition team consists of 12 members with backgrounds in software development, electrical engineering, mechanical design, and embedded systems.
To keep the payload light, we decided to carry 2 water bottles at a time. The aircraft will land to reload remaining water bottles as well as swap batteries mid-mission. Thus, the aircraft would need to have a flight time of 10 plus miles and flight speed of 17 meters per second. This will ensure that we can complete a high number of bottle drops within our 30-minute mission demonstration window. To achieve this flight speed, our control surfaces must generate enough force to achieve the desired banking angle for the required turning radius of 150 feet. The battery must also be large enough to provide power for 10 miles of flight. Setting the exposure time of our camera to around 383 microseconds reduces the ground smear flying at 12 meters per second to below our ground sample distance of 0.46 centimeters per pixel. This will allow us to acquire images clear enough for object detection. At 75 feet, 8.5-inch targets will be around 47 by 47 pixels. This will be enough to resolve a target.
We have designed and built a new vertical takeoff and landing aircraft this year. The aircraft weighs 9.8 kilograms and can cruise at 18 meters per second for 90 kilometers with one takeoff and landing. The aircraft has been designed to carry interchangeable payloads, one of which is the guided parachute system for the SUAS competition. The system can hold 2 water bottles at a time. For imaging, we use a Lucid camera attached to a Raspberry Pi. This is then transferred via our antenna tracking system to our ground control station. Our ground control consists of custom-written software to view and process images, as well as perform mission objectives by interfacing with Mission Planner. We utilize 3 machine learning models to detect and classify standard and emergent objects. To detect standard objects, we fine-tune a YOLO V8 object detection model using a synthetic dataset to reduce the need for data collection and modeling. We generated the dataset by using OpenCV to place different shapes and characters on a pavement background, and assign bounding boxes accordingly. We used the object detection model to detect the shape and color of the object, then feed it into the Parsec text recognition model to read the character from the detected shape. To detect emergent objects, we also utilized the YOLO V8 model, which is pre-trained on the COCO dataset, which includes humans as its class. When using the model for prediction in the competition, we are taking high-resolution images of 5472 by 3648 pixels that cover the whole runway area where the target will be placed. We will slice the image into smaller chunks before feeding it into the YOLO V8 model, since it is trained on small images, roughly 640 by 640 pixels, and if we feed the full image, the individual object will be very small. Then we combine the detection result and make the airdrop decision. The camera we are using is the PHX-200S made by Lucid Vision Labs. The sensor has a pixel size of 2.4 by 2.4 microns, and our lens has a focal length of 12 millimeters. This gives us a ground sample distance of 0.46 centimeters per pixel. An 8.5 by 8.5 target at a height of 75 feet should have a resolution of around 47 by 47 pixels. Our approach for this year's airdrop task is to use GPS-guided parachutes. These are loaded onto the aircraft and deployed by our in-house designed payload release controller. The whole payload subsystem consists of 2 parts, the payload release controller and the payload itself. This year's payload is our first time designing a flight controller for parachutes. The system consists of a cruciform parachute, a custom designed flight controller, and a steering system. Flight controller is comprised of a microcontroller, a GPS module, an inertial measurement unit, a pressure sensor, an onboard power distribution system, and an SD card system to log telemetry data. The steering system consists of 2 360-degree rotation servos with an optical encoder to provide feedback. The servos pull 2 of the strings attached to the parachute. By retracting either string in an asymmetrical fashion, we can control the yaw of the parachute. By retracting both symmetrically, we give the parachute a forward bias. The parachute control algorithm is simple to understand. The payload's heading and distance to the drop point is fed into the control system, which outputs servo positions that steer the parachute to the destination. The system uses a PID control strategy along with a 6-axis Kalman filter to predict and estimate the current position and velocity in the NED frame for reference. The release controller is mounted onto the aircraft's belly. The system communicates with the onboard flight controller and aircraft computer to deploy the parachute. It consists of an ESP32 microcontroller and servos. The release controller queries the ODLC system for drop location and payload type. Then, it calculates an optimal release location based on factors such as aircraft speed, wind, and mechanical delay. Having determined this, the release controller communicates the drop points to the payloads over Wi-Fi using the ESP-NOW protocol. The rapid release mechanism uses servos and elastic straps to secure the water bottle and parachute. When we reach the drop point, the straps snap back instantaneously to release the payload. We used physical airdrop test data combined with simulation to more accurately represent airdrop tests conducted in different conditions such as varying wind. In 100 trials, we achieved an accuracy of 84% with the 90th percentile being 7.34 meters.
A radio communication system consists of two components. One, a low-bandwidth text-based system at 900 MHz for basic communications and controls, and two, a high-bandwidth image telemetry system at 5.8 GHz. The low-bandwidth system uses 902 to 915 MHz band and operates at a maximum of 1 watt, with a maximum EIRP of 4000 milliwatts. It uses proprietary RFD 900X modems with 6 dBi antennae. For it, we expect a line of sight range of 15 kilometers. We have tested this system reliably at 5 kilometers for several years. The high bandwidth image telemetry system uses standard Wi-Fi equipment and transmits with the UNII-3 band, which consists of 5.735 to 5.825 GHz frequencies. It uses two Wi-Fi adapters to achieve high data rates. A 6 dBi antenna is used on the drone and a high-gain 22 dBi antenna tracker on the ground. At the anticipated transmission power of 16 dBm, this system has a maximum EIRP of 4000 dBm, thus abiding by the FCC regulations. We expect a throughput of 30 megabits per second at a range of 2 kilometers. We have not tested this system at its full range of 2 kilometers due to location constraints. Instead, we have tested it at reduced range and reduced gain. We discovered that transfer speed of 60 megabits was achieved at 60 meters when using 6 of 22 dBi of gain, which we were using with TCP protocol. With the 22 dBi antenna, this could translate up to 60 megabits at 380 meters using TCP. This data rate is significantly lower than what we anticipated, and upon further investigation, the quality of USB Wi-Fi adapters were found to be the issue.
For the design of our project, we designed a wing and airframe around the idea that the aircraft would be capable of a vertical and horizontal flight. The values that we first decided on was for the aircraft to be able to fly 10 plus miles on a single battery charge and weigh less than 10 kilograms. The first portion of the design was deciding on an airframe layout for the quad plane. The highlighted portion on this top-level view corresponds with the load-bearing carbon fiber spars in our design. The front spar in the front of the motor was not originally part of the initial design, but was later added to increase the stiffness of the airframe. For designing our wings and control surfaces, we went through a selection process to find airfoils that were easy to manufacture and had good flight characteristics. We compared different airfoils by looking at coefficient of lift versus angle of attack, and coefficient of lift versus coefficient of drag, also versus angle of attack. The airfoil we settled on struck a good middle ground between being high performance while being reasonable to manufacture. For our 3D analysis, we iterated through various chord lengths, wingspans, and tapering ratios, eventually converging on a design that had a small enough wingspan while providing us enough lift. Parameters such as taper ratio and aspect ratios were optimized, while also aiming for an overall elliptical lift distribution to maximize the wing's efficiency. Selection of vertical motors was done by comparing the power efficiencies of various motor and propeller combinations, which would give us a total of 10 kilograms of lift. The chosen combination was 4 U8 Light KV100 motors equipped with 22-inch props. Our horizontal thrust motor is a KV170 with 16-inch props. The battery we chose was a 5000 mAh 12S LiPo. The main advantage of this specific battery being that it was very long, which helped to give it a very small cross-sectional area. This was important as this allowed us to fit it within our inboard wing, which helped with the aircraft's weight distribution. Here is the fully complete assembly of our CAD. Fabrication involved exporting a flat surface of each part, and then water jet cutting or laser jet cutting them. Joints were manufactured using a water jet cutter, with most either being aluminum or carbon fiber. The wing was made out of balsa wood, with the inboard airfoils being made out of carbon fiber balsa core for added strength. The wing and tail were assembled separately and then later joined together. Various flight tests were first performed in vertical modes to ensure safe and reliable vertical flight before testing transitions to horizontal. After ensuring that the aircraft is able to maneuver well in vertical flight modes, we began testing VTOL transitions. Afterwards, we fine-tuned parameters like how much assistance the vertical motors would provide in order to meet our desired flight range and to meet the turn-in radius requirement of 150 feet. Completed aircraft had a takeoff weight of 10 kilograms and a flight range of 8 miles. Our average cruising speed is up to 17 meters per second at a flight time of 9 minutes while in vertical flight and 22 minutes while in horizontal flight. Overall, we tested the aircraft over 27 flight tests with a total flight time of 165 minutes. 12 of those flights were autonomous, with 90 minutes spent on autonomous modes.
Autonomous flight is performed by utilizing a Cube Orange with Autopilot and 3 separate services: Mission Planner, MPS, an abbreviation of Mission Planner Scripts, and GCOM, an abbreviation of Ground Communications. MPS is a REST service that allows for control of our VTOL through an HTTP API, enabling our software systems to plan and route missions and toggle features such as the flight mode, altitude, and collision fencing, which is when the UAS dynamically avoids marked zones in its waypoint queue. GCOM is made up of a backend written in Go and a front-end written in React. It provides a user-friendly GUI for drone monitoring and sending waypoints. Since waypoints may be added dynamically during flight, MPS supports adding and removing waypoints to the waypoint queue. During the development process, we utilize an in-house version of SITL, a dynamic software-in-the-loop system which helps us simulate our competition drone's parameters. We fine-tuned these simulations parameters to ensure that when it came to performing with our drone, we ran into no issues. This was the central environment for testing the waypoint system. To test autonomous behavior in the field, we performed tests using our legacy drone Hummingbird. With these tests, we verified fully autonomous takeoffs, landing, and waypoint paths with 5+ required waypoints. Once the competition VTOL was complete, we performed similar waypoint tests with it to verify complexities such as transitions from fixed plane to quadcopter mode. The statistics of these flights are as shown here.
The VTOL utilizes the MPS service to route around areas that may contain obstacles or exclusion zones. Given a set of coordinates defining a polygonal area that we want to avoid, which is indicated by the red boundaries of the diagram, the algorithm wraps a convex hull around the area representing the minimal distance path around its parameter, which is represented by the light green boundary as shown here in the map. It then accounts for the entry and exit waypoints, which are the blue dots showing the original course, and plots a new course, choosing to divert either left or right around the obstacle, depending on which path is shorter. The exclusion zone functionality was tested using our SITL, which stands for Software in the Loop, environment, as you can see in this demo footage. Once the tests were consistent in simulation, we performed a series of additional tests in a similar fashion for the Autopilot designs, by running the same flight plans using our Hummingbird aircraft. Our system also employs a multi-stage approach using the point cloud library to process LiDAR data for obstacle detection and avoidance. First, we reduce noise by iterating through each point in the point cloud and removing those intensities below a predefined threshold. Euclidean cluster extraction is then utilized to group nearby points in the obstacle and plane clouds into clusters based on spatial proximity. Finally, the minimum volume bounding box is drawn for each cluster using the oriented bounding box algorithm, which then calculates dimensions and orientation of the bounding box to use for obstacle avoidance and navigation.
While we initially considered a quadcopter design for our UAS due to benefits such as modularity, we ultimately rejected it due to efficiency issues of utilizing multiple motors at significant throttle for a prolonged flight. Traditional fixed-wing aircrafts are much more energy efficient due to more productive lift generation, and with the use of a VTOL, a vertical takeoff and landing configuration, we get the benefits of both types of aerial systems. Different wing configurations were also considered, including a flying wing, high wing, and parasol configuration. Ultimately, we decided to go with a parasol wing design, as they are extremely stable and have a gap that allows for the payload to be repositioned, which allows for an easier center of gravity balancing. Additionally, this modularity allows for the aircraft to fly with a variety of different payloads, if needed.
UAS is aware of the safety risks associated with developing an unmanned aerial vehicle, and has taken steps to mitigate them. During development, areas where flight and airdrop tests were conducted were cleared of people and secured as required by our airspace authority. We implemented hardware and software devices to reduce the chance of injury or damage, such as arming plugs and robust fail-safes in case of a lost connection to the aircraft. These safety measures also apply to the mission. In addition, all personnel on the flight line will rehearse their roles and procedures in response to unexpected circumstances.
After running 4 missions, this is our expected overall performance for each of the scoring criteria. For each of these tests, we run simulated missions which involve doing waypoint laps, detecting target objects, and then performing a bottle drop at a specific location. During each of these tests, we were able to hit all our target bottle drops, and simulated testing puts our image detection accuracy at about 90%, which is at our desired height and flight speed.
Our pilot is Charles Sorianto, and he can be seen flying our Albatross VTOL aircraft. Pictured is our manual 1,000 foot from home flight. As you can see, we have exceeded the 1,000 foot requirement from home, since 1,000 feet is just under 305 meters as indicated on screen. Here we have configured a waypoint mission in Mission Planner. Charles first arms the aircraft and then switches the mode to auto to let the drone fly on its own, as shown on screen. Here you can see us far surpass 200 feet from home, as 200 feet is just under 61 meters. Charles now switches to Q loiter, which is a manual mode, and proceeds to land the aircraft. This is our autonomous flight to show we are able to meet the flight performance requirements. As a start, we are able to take off well within a runway space that is 70 by 75 feet. Additionally, since we have a VTOL aircraft, our angle of climb and descent well exceed the 20-degree minimums. Throughout the flight, notice that we remain over 75 feet above the ground, which is a little under 23 meters, when more than 200 feet away from the runway. Additionally, the waypoint error margin was set to 7 meters, which is just under 23 feet. Meeting the under 25 foot requirement. Note that we switched to manual flight here out of caution due to the strong winds and proximity to the trees. We then completed the remaining 600 meters by manually flying around and then landing. Here you can see us reaching 8.05 kilometers, which just exceeds the 5-mile requirement. UAS is ready to meet the challenges brought on by the SUAS competition with its new VTOL aircraft and guided parachute system. With the use of machine vision for ODLC and custom ground control software, we've centralized control over all of our systems. Furthermore, through our extensive subsystem and full mission tests, we've validated the functionality and safety of our systems. We are confident in our competition readiness and can't wait to see you on the flight line.